Hi, everyone. Today we're going to continue our discussion of multiple logistic regression and looking at how to use that type of model with R. So last video we talked about fitting the model in R, interpreting some of the regression coefficients, and how to check if various assumptions or conditions for the model are met. And so today we're going to continue with talking now about hypothesis testing, conducting statistical inference of our regression model, of our logistic regression model, and then looking at how to select our final model given several candidate models at our disposal. So to start, just like with multiple linear regression, we can construct confidence intervals for the regression coefficients for our logistic model. If you recall before, we had beta hat, the regression coefficient estimate plus or minus a confidence interval multiplier times a standard error estimate. So this is very similar to the format we've seen previously for multiple linear regression. The main difference now is that instead of a t-star multiplier, we have what's called a z-star multiplier. And so that has to do with distributional assumptions that these models rely on. So the confidence intervals for multiple linear regression relied on quantiles from a t distribution to get the t-star multiplier. So that's why it was denoted with a t. It's not too important that you know that for this course, but just for statistical theory, if you ever go on to take a course in that. Whereas this z-star multiplier is denoted with a z because that's commonly how we denote quantiles of a standard normal distribution. So this is representing that. Okay, and so we can construct a confidence interval for each regression coefficient where we have several of them. So here we're assuming we have k number of candidate predictors. So for z-stars, the multipliers, they only depend on the confidence level. So a t-star multiplier for multiple linear regression depended on two things: the sample size, which determined the degrees of freedom, and the confidence level. You can make a 90% confidence interval or a 95 or a 99. All those things would change the t-star value. Here, z-star does not depend on the sample size. It only depends on our confidence level. And so for the most commonly used confidence level, which is 95%, z-star is always 1.96. And if you're, again, where does that come from? So I can show you real quick using R, actually, if you wanted to calculate it yourself. It's based on an integral using the probability density function of the standard normal distribution, which is a lot of jargon, stats, math stat jargon, but pretty much we can get the quantile of a standard normal distribution here using this Q norm function. Okay, and looking at the help file here just to make sure I have the syntax exactly correct. So what we're going to do is say p equals 1 minus, for a 95% confidence interval, we're going to say 1 minus 0.95, like this. Okay, and that's it. We keep the other parameters the same because that's for a standard normal. And so here, so for if you wanted it for a 90% confidence interval, you would just substitute 0.90 here. And so here we see this is goes out to many decimal places, but if you rounded it using the round function in R just to 3 decimal places, it ends up being 1.96. So people just round it off there and just say use 1.96. So anyways, long story short, if you're wondering where that comes from, you can find it manually using R yourself if you wanted to. People, not too long ago, even when I took intro stat, just, let's see, how long ago was that now? Maybe like 7 years ago is all. We would look these values up in tables these Z stars and T star values because that's how they did it back in the day. They just had giant tables with these values in it. But now we can calculate it just like that using R. So stuff's a changing all the time for the better. So yeah, so that's the Z star multiplier here. And we get the beta hat, the regression coefficient estimate, and the standard error estimate from our model output when we print that logistic regression model output. Okay. So that was how to do a confidence interval. Hypothesis tests, again, are similar to the format we've seen for multiple linear regression. So we can test if a regression coefficient is 0 or not using a Z test statistic. So just like before, we got a T test statistic for the hypothesis test. For multiple linear regression, for logistic regression, we get a Z test statistic. And so this is the same format, the coefficient estimate over its standard error, but how the p-value is calculated based on this differs. That's why it's denoted with a Z, because this uses again, a standard normal distribution to get the p-value rather than a T distribution. Okay, and we can again test this for each of the predictors individually, where we have K predictors. So we can construct the confidence interval ourselves by getting each of these pieces and then doing estimate plus or minus the margin of error, this quantity over here. But we can also, using some handy functions in R, get those confidence intervals directly. So especially using this summary function from the JTools package, we can get that. So by specifying this option confint for confidence interval equals true, capital T, and then specifying the confidence level, which I think defaults to 0.95, but I wanted to show you how you could change it if desired. Okay, and then this model.info equals false. It just gave a lot of output that wouldn't fit on the slide, so I suppressed extra output because we're just interested in these confidence intervals mostly for now. So looking at the regression output here, so just as a quick reminder from last video, we were modeling the probability of an email being spam using the longest, the number of characters in the longest all caps word in the email. So for example, maybe the longest all caps word was hello, in which case there'd be 1, 2, 3, 4, 5. Max length would be 5 because hello has 5 characters, if that was all caps. Okay, and we considered using a log transform after looking at the empirical logit plots and seeing that linearity assumption was not met. So log transformation tended to help that. So that's why we chose that. So this is the log max length as our predictor, and we're modeling the probability of an email being spam. Okay. So getting a 95% confidence interval for the coefficient for this predictor. These are our values here, 0.928 to 1.059. Okay. So we can exponentiate this prior to prediction, which is what we want to do for logistic regression. These coefficients and the confidence intervals are on the log scale. So we actually want to calculate what these exponentiated bounds are, the lower and upper bounds on our interval. So using R, we can, only wants me to do one at a time. Oh. Now I see what I did wrong. Okay, so using R, or you can use a regular calculator or Google, we can get these bounds. So looks like 2.53 and 2.88. 2.53 if we round, and 2.88. Those are our bounds there. And then we can proceed to interpret those values. I'll just skip to the next slide because you can actually, in this JTool sum function for summary, we can actually specify ask it to exponentiate those things for us. So using exp equals true, adding that option. So then you can see here 2.53 and 2.88, it gave us those exponentiated estimates already. Okay, so that's great. So now I'll give an example of how to interpret this confidence interval. So CI confidence interval interpretation here. This is a interpretation for this confidence interval. We are 95% confident that for every 1 unit increase in the log max length of an email, the units get a little bit messed up because of the log here. The odds of the email being spam multiply by between 2.53 and 2.88. So again, want to point out that the increase in the predictor value affects the odds on the multiplicative scale. So the odds of the email being spam multiply every time by about 2.5. Okay, so then if we add one more character to the longest all caps word, odds of the email being spam multiply by 2.5. If we add a second character, it multiplies by 2.5 again. Okay, so in other words, for every 2 characters longer, the longest all caps length word is. For every 2 longer the log all caps word is, the odds of the email being spam multiply by about 6. Okay, so you can't just add 2.5 and 2.5 for a 2 unit increase like we did in multiple linear regression. Now it's on the multiplicative scale. Okay, so it's a little bit different for logistic regression. Also, again, want to really emphasize that this is not talking about the probability of the email being spam multiplying by this. This is talking about the odds of the email being spam, okay? And these are slightly different because P, and sorry, I know I'm emphasizing this a lot. It's just a common mistake that's easy to make when doing logistic regression. P is the probability of success. Odds equals P over 1 minus P, the ratio of the probability of success and the probability of failure. That's what the odds is. So so although as the probability of success increases, so does the odds, it's not necessarily, we can't say that it's not that if the odds multiplies by 2, the probability multiplies by 2. That is not true, okay? Because actually, if we look at the relationship between the two, P equals the odds over 1 plus the odds. If you solve using this equation up here, you would find this relationship holds. So you can see if the odds multiplies by 2, then P kind of multiplies by 2, but it's not exactly. So we can't just substitute probability instead of odds in this interpretation because that's not exactly true. So anyway, these equations and relationships are important to think about and keep in mind when doing these interpretations here. Okay. So using this fitted logistic model here, we can look at how well does this logistic model, if we apply and get the predicted values for our whole data set, whether an email spam or not, how well does it do in predicting values for the data set that it was fit on? So ideally very well, but not necessarily perfect, and that's okay. If anytime a model claims that they perfectly predict the outcome in their whole data set that the model was fit on, you should be skeptical about overfitting having occurred. Your model should not do perfect on the data it was fit on. That's very unusual and indicates your model will likely do poorly on new data that it was not fit on. So anyway, using the caret package here, and so if you want to run this code yourself too, you'll have to install that packages caret prior to loading it using the library statement. You'll have to run that in R. So using this caret package, we first get the predicted values, and then we can create a confusion matrix, which is a table showing how successful our model was in classifying different outcomes. So this is the confusion matrix here. There's a lot of output here, but this right here is the confusion matrix. Okay. Find my typing. Okay. So this confusion matrix is telling us that here's our what our model predicted, and then here's what was actually occurring in the data set in the columns. So for 2,563 of the emails, they were truly spam. Okay. Or actually, this is I think this yes no is whether if it was not spam, which is a little bit weird. Yeah, I don't think we had that many spams in the data set, so it looks like it got flipped, but that's okay. So it looks like about 2,600 of emails were not spam in the data set, and our model correctly got those correct. Conversely, well, maybe that's the case. Anyway, 777 of the emails that were not spam, our model got correct as well. And then we can see there's 1,200 total that it misclassified, okay, out of everything in the data set. So this model output is also telling us just overall it was about 72% accurate in classifying whether an email was spam or not. That's not too great, to be honest. I mean, you can think if you just did a 50-50 coin flip for each email, you would end up being right about 50% of the time. So you definitely want your model doing better than at least 50% accuracy whenever doing a binary classification problem. Otherwise, that's a huge issue. Your model's worthless, essentially. So here it's doing a little, slightly better than 50-50, but not that much. So, and it of course depends on the context of the problem. Some settings, it's much harder to do better than 70% accuracy or so. That's just how it is in certain settings. For example, I think like predicting college basketball games, I think it's generally accepted. It's really hard to get above like 80% accuracy in the long run for games, just because there's so much variability in the outcomes in general. Not everything's deterministic in real life. So anyway, so that's what this confusion matrix is telling us. So that was using this was the model where we did not log transform the max length, but we can look at the confusion matrix for the model where we did log transform. Okay, so that was spam fit 3. And we see our model improved. We get a bit higher about 1% higher classification accuracy. So that seems like not much, but given how big our data is with thousands of observations, a 1% increase in accuracy can make a huge difference. Someone pointed out in one of the predictive modeling classes I took in grad school that like Netflix had like a competition where they were trying to get people to have accurate classification models, and somebody got like a 2% increase in the accuracy above what Netflix was already achieving for their competition. And that brought in like an insanely high amount of money for Netflix. Even though it doesn't sound like much of an increase in the prediction accuracy, if you have thousands or tens of thousands or hundreds of thousands of observations, a 2% increase in the accuracy can make a huge difference for the company or whatever your goal is. So anyway, so it looks like this log transformed model gave us a little bit better results. Okay. So moving on from that, now we can revisit how to select our final model given some candidate models. So like in this case, yes, the log transformed model appeared to meet the linearity assumption better. It appears to be more accurate when applied to our whole data set. So those suggest that that log transformed model is best. But it wasn't the only predictor we had available. And there just gets to be a lot of choices for which model to use. Do we include all available predictors? Do we include their interactions? Lots of questions. So one way to decide which predictors to include is, again, to use this, this technique called cross-validation, or CV. And just as a quick reminder, for cross-validation, we use training data. We set aside a subset of our full data set to train our model or to fit our model on. And so using the data that we did not fit our data on, which is called a test set, then we see how well our model fit on the training data does for predicting the outcomes in the test data set, in that other subset of the data. Okay, and the idea is this will give us an idea for how well our model will do in predicting future data that wasn't used for fitting. Because in general, a model will do better for predicting the data that it was fit on, just because that's the data that it learned the relationship through. So it'll artificially do better than it will do in practice for unseen data. But cross-validation tries to get around this issue. Okay. A commonly used version of cross-validation is five-fold cross-validation. So that's where we separate our data set into 5 partitions or subsets. Okay, so they're partitions because they're completely separate from one another, these 5 pieces of the data. And we fit a model 5 times. So each time using a different 80% of the data, a different 4 partitions of the 5 partitions to train our data on. And then we predict for that left out partition of the data, that left out 20% of the data, using 5 different test sets, the 5 different pieces as test sets. Okay. And so we repeat this for each of the 5th of the data. And so each time we can get like a metric of like how well did we do in predicting the outcomes for that test set. Okay. In this case, for logistic regression, it's how accurate, what was our accuracy is the commonly used metric. What was our accuracy on predicting the outcomes for the test set? You can think about how we saw how this can be applied to multiple linear regression, where we look at what was our mean squared error, our MSE, on predicting values for the responses in the test set. But yeah, now we're doing what's the accuracy. Okay, and then we average across those 5 accuracies in this case to get an average accuracy on the test set. And the idea is we select the model that has the highest accuracy across these 5 test sets. Okay, and this again helps prevent overfitting, because if a model tries to learn, ends up modeling some of the noise in the data rather than the true relationship, cross-validation will be more likely to weed this out. And the idea is like it might do really well in the training set if it's overfitting, but then it'll do poorly on the test set if it was just modeling noise that's in the training set. So that's how cross-validation can be helpful here. Okay, and sort of visually, this is how it might look if we had, say, 100 observations. So we have our full data set. It has, say, 100 observations. We split it into 5 pieces. So the blue is representing our training data. And then each time we get a classification accuracy for predicting the responses in this test data set. Okay. So each time we'd fit on 80 observations and then predict the classes for the 20 left out observations. So this is just a quick visual of cross-validation here. Okay. So let's suppose we're considering 6 different models that we want to consider. And we want to compare them. We're going to use cross-validation. So we had two total predictors, max length and total length, where total length, I think, was the total number of capitalized characters in the email, and then max length was the number of characters in the longest all caps word in the email. Okay. So we could use just a simple logistic model with either one of them as the predictor, use a 2-predictor logistic model, log transform either of them, or log transform both and use them. So all of these are candidate models. Which one is the best? That's where it's hard to decide. Well, let's use cross-validation and see how that goes. So first, what I'm going to do here with this R code is I am creating these formula objects for each model, which represents the relationship in the data that we're going to model. Okay, and this corresponds to these 6. It's in the same order. First one is just max length, total length, the 2 predictors, log, and then both predictors log transformed. So these are stored in a list, and then using this lapply function, which stands for like apply to a list, lapply, I'm going to fit each one of these logistic models, and I'm specifying that I want family equals binomial for the logistic regression model to be fit. And then I'm storing it in this object canned mods to represent my candidate models. Okay. Now, so I fit each of those 6 models and stored it in this list of length 6, this canned mods object. Now to look at the cross-validation accuracy for each of these models, I load the boot package from R that allows us to use the cv.glm function, cross-validation for generalized linear models. So again, just like for the other times we use R packages, you will likely, the first time you run this on your machine, if you haven't already, you'll have to install the boot package prior to loading it using this install.packages boot code here. Okay, and then similarly with the tidyverse here. Tidyverse code or package is really big, so it will take a bit on your machine to install that probably, and that's okay. Okay, and then for this cross-validation cv.glm function, it has like what it calls a cost function that it wants you to input. So I'm using accuracy here to measure the accuracy across the cross-validation folds. There are different loss functions or cost functions that you can use. For example, there's the, just to look at a couple here, there's the log loss that sometimes people look at. And let's see if this Kaggle post talks about it here. Okay. So accuracy, and they don't really give a formula for it here. Accuracy is certainly the most intuitive and I would say commonly used function here. The log loss, yeah, the log loss right here is a little bit different. Yeah, so it's given by this weird, maybe that's not the log loss. Anyway, we're not going to use log loss in this class, but there are certainly other functions we can use besides accuracy, but we're just going to be using classification accuracy across the folds here. And so this function allows you to specify different loss functions if you want. And then I specify k, which is the number of cross-validation folds that we want to specify. The most you can do, if you think about it, what's the most folds you can use for cross-validation? So the biggest number of folds you can use is the number of observations in the data set, because we have to leave at least one observation out for our test set each time. So we could have, if we had 100 observations, we could do a 100-fold cross-validation. And in fact, they call that specifically leave one out cross-validation. But anyways, here we're doing 5-fold cross-validation. We get the accuracy across the folds for each of our 6 models using this supply code. And so, yeah, so we want the model with the largest cross-validation accuracy. Here it's close, but it looks like model 4 has the highest. Okay, and if we look back up, which one was model 4? Model 4 is just the model with the log max length. So again, not the model with the most number of predictors, and not the model that was not log transformed. It happens to be this model 4. That's what cross-validation thinks is the best. So, but cross-validation, again, is not the only way to select a model. I think it's the best way myself, but there are other approaches, such as AIC and BIC. So using this code here, we can calculate the AIC and BIC for each one of these models. And we want to select the model with the smallest AIC and BIC. So here, that is very close, but it is model 4 again. So AIC and BIC both imply model 4 is the best, which aligns with cross-validation here. So that's great. We have a nice cohesive story. Model 4 is our best, which is the log max length model. Okay. So even though, like I said, I prefer cross-validation myself, it is computationally more expensive than AIC and BIC. So when we do cross-validation, we have to fit the model 5 times because we have to fit it for each fold of the data if you're using 5-fold cross-validation. If you have to do if you're doing leave one out cross-validation, you have to fit the model n times, where n is the number of observations in your data set. So you can see where that gets extremely large. If you have like 1,000 or 10,000 observations, that can start to get to be where, even though computers are really good, it might take a while. So AIC and BIC is based on some stat theory calculation, and it's based on the model having been fit only once ever on the full data set. So these can be helpful in like big data scenarios, I suppose, more than cross-validation. So yeah, so our final model that these approaches selected was this log max length model, which we saw before. And so here's the model output without exponentiating the coefficients. If we want to interpret them, usually easiest to exponentiate them. Okay, and then here I'll just give a interpretation of the beta hat for our model. Okay. So first, I guess I'll interpret the interpretation of the estimated intercept. So since 0.36, and I'm going to use R, calculate this value. round that off. The odds of an email being spam, of an email with a max length of 1 character being spam, and that is because log max length being equal to 1 implies that, or I'm sorry, for 0, the intercept is when the predictor values all have 0, implies that max length equals 1. And so that's since e to the 0 is 1. And e to something is how we undo the log function here. Okay, so since e to the 0.036 equals that, the odds of an email with a max length of 1 character being spam are about 1.3037. That is the probability of an email with the probability of an email with a max length of 1 character being spam is about, and important to note, it's the estimated probability. Okay. And then the odds over 1 plus the odds gives us the estimated probability. Okay. Again, I'm going to use R to get this. Right. Estimated probability of an email with a max length of 1 character being spam is about 0.5. So a 50-50 chance in this data set. But that's how we interpret the intercept term here. For the regression coefficient, since e to the 2.7, oh no, I'm sorry, this is already, this is already exponentiated. Oops. I'll forget what I just said. Okay. Okay, so we didn't need to exponentiate it. The odds of an email on the max length of 1 being are about, okay. Sorry, didn't need to exponentiate it. So hopefully you caught that sooner than I did. Okay, so redoing this calculation, I was like, man, that seems high. Okay. Very unlikely that an email is spam in this data set. Okay. So the estimated probability of an email with just one capital letter in its longest all caps word being spam is about 0.03% chance. Okay. All right. And for the estimated regression coefficient, since beta hat equals So since beta hat equals 2.7 for every 1 unit increase in the log max length, again, the units get a little bit messed up because of the log transformation here. The estimated odds of an email being spam multiply by about 2.7. Okay. So that's how we interpret the regression coefficient estimates that we have here. All right. And that wraps it up for this video. So thanks, and talk to you guys again soon.